All right, we're back with another episode of How the Heck Do You Do That? Where we're going to work out the math of some kind of physics. In this case, we're going to try to figure out how to get a satellite in geosynchronous orbit. Sometimes this is desired for certain types of communication satellites and whatnot. So we're going to try to figure out how far away does it have to be from Earth, and what speed would it be traveling once it gets there in order to stay in that orbit. So as far as some of the things we know, I've already pre-filled this stuff in. We know the mass of the Earth. That's pretty readily available information, and we know obviously the universal gravitational constant. We are not given the mass of the satellite, so I'm just leaving that right now as m sub s. We'll come back to that later. I've also included, of course, a diagram of what's going on here. We've got the satellite being attracted to the center of the Earth. And if I want to know what's going on with that satellite, of course, I would draw a free body diagram. So if I look at just the forces acting on that satellite, I've got the force of gravity between the satellite and the Earth acting on that satellite. Why do I need to know that? Because you guessed it, we're going to be making an FBD here pretty soon too. There's one other piece of information we know. In order for it to be geosynchronous, that means it stays over the same spot of the Earth at all times. In order to do that, it would have to have essentially the same period as the Earth, which we know happens to be 24 hours. So in other words, that satellite is going to be circling the Earth once every 24 hours so that it's constantly over the same spot on the Earth. So with that information, I also know the period of the satellite, 24 hours, and all I did is I did a quick conversion here, knowing that every hour takes 3,600 seconds, and I figured out how many seconds it's going to take for that satellite to make one orbit of the planet. So now, as I mentioned, I did my free body diagram. Where does that lead me? It leads me to FBD. So I go down here, and we sum up the forces acting on that satellite. Well, this one's really easy. In this case, there's just the one force acting on that satellite to keep it in a circle. The clue is the fact that it keeps it in a circle. That tells us that the net force results in a centripetal force, which is given by the equation mv squared over r. How many forces are providing that centripetal force? Well, right now, just one in this case. And that is according to Newton's universal law of gravitation. So it is the force of attraction between the Earth and the satellite at that given distance. So now we've got our force summation. We've got the centripetal force being caused by gravity. All right, so now here's what we're going to work with, is this part here. One problem. I actually have an equation now with two variables because I don't know the speed of that satellite, and I don't know the distance away from the Earth. I don't know either of those two things. However, this is where we go back to our information about centripetal force, and we remember that since that satellite is traveling what we are assuming to be a circular path, we know that the speed, which is distance per time, well, the distance around that circle is going to be 2 pi times the radius of the circle. And we know that in the case of an orbit, it's going to take one period to get around that circle. So we've got a distance and we've got a time. So there's our speed. So now what we need to do is we need to take this and we need to plug it into here for that. So doing that, doing a little bit of algebra here, we've got that over that times 2 pi r over t, and that quantity is squared because the original quantity was squared, is equal to all this stuff over here. Now, we got to remember here that since the object in orbit, since the object in that circular motion is the satellite, that's what mass is that's the mass referred to in the centripetal force equation. Well, as soon as I do that, I see that I've got the same thing on both sides, so those cancel out, and I'm left with just expanding this out. 4 pi squared r squared over t squared is equal to that times the mass of the Earth over r squared. Okay, very quickly we're going to do some cross multiplication to get this simplified a little bit. Oh, and I almost forgot that down there. All right. So, and I can do a little bit of cancellation already. This down here is going to cancel out with one of those. So now I get to my cross multiplication, and on one side I will have 4 pi squared r cubed. I'm going to set that equal to my other cross multiplication, which is g times the mass of the Earth times the period squared. Don't forget, we're trying to figure out how far away that satellite needs to be. So to get that isolated by itself, I need to take that times that times that all over 4 pi squared. And since I don't, the radius cubed does me absolutely no good, so what I need to do is I need to take the cube root of both sides. So when it's all said and done, the distance that that satellite needs to be from the Earth, or from the center of the Earth I need to specify, is given by this expression over 4 pi squared, and we have to take the cube root of all of that. And then it's just a matter from there, it's a matter of plug and chug. I plug in the variables and pop out my number. All right. Now, the further question is, remember, if we go back up here, how high does it need to be, and at what speed? Oh, by the way, don't forget this radius here. That is from the center of the Earth. So in this case, both on the Mastering Physics question and the example that was given in the book, it actually asked you what altitude above the Earth's surface. No problem. If I want to know the altitude above the surface, I would just take whatever this answer is. That would be the total distance from the center of the Earth out to that satellite, and then I would subtract the radius of the Earth, and that would give me whatever left would be that altitude that that satellite needs to be above the surface of the Earth. Now, the other question was, well, all right, now we figured out how far away from the Earth it's going to be. What about its speed? How are we going to do that? Well, we go right back to our force summation, our original force summation, which equated the centripetal force was being caused by the gravitational force pulling towards the center of the Earth. So with that in mind, we go right back to the centripetal force is equal to the force of gravity. Again, that's the satellite, and that force of gravity between the satellite and the Earth over the distance squared. In this case now, again, those two things cancel out, same on both sides. Now we just want to know that. Oh, and by the way, this will cancel out with one of those. So now we just rearrange to solve for that. It's already taken care of, actually. Is equal to that times the mass of the Earth over, oh, my bad, over, because we already canceled that out, over the distance to the satellite. All right, and again, if I want to find the speed, then I just take the square root of both sides. So when it's all said and done, the speed of that satellite is going to be given by the expression of universal gravitational constant times the mass of the Earth divided by the distance away from the center of the Earth. Remember, that's important there. And then the square root of that quantity. So hopefully this helps you out working through that. The key there, I honestly believe, is remembering that based on the force diagram, that the force of gravity is responsible in this case for the centripetal force. Everything else comes from that. All right, if you got questions, ask me in class. Hope this helped.